welcome back to my stream. I wasn't able to stream yesterday, but I am up and running today. This is good. I need to switch the screen over. There we are. So yesterday we left off working on the generate AST. Last time we left off with this. We actually have code now that when we run cargo build, it executes this build.rs, which calls generate AST, which is in here, which generates a file based on the name of the type, and it creates a file that looks like this, source Expr. There. So this file is automatically generated. While we were doing this, somebody in chat suggested it could be done with a macro instead of writing code which generates code, which, you know, macros are exactly that, code which generates code. And then just before I ended the stream, this was pasted. It was after I had already transitioned to my end slate. But this is code that Mizzard in chat pasted a link to, and it is a macro which does the define AST and generates code that looks exactly like, well, mostly exactly like the code that we're generating here. You can see the enum Expr, the structs, the trait is there, all the impls are there, and then there's these things up here as well, and I'm not sure what those are for. But this is the whole macro. It fits in 31 lines of macro code. And I don't know Rust macros that well to dissect this, but I can sort of see how it's working, right? We have the type ident / visitor ident, which is the Expr and Expr visitor, which is here, pubenum Expr and pubtrait Expr visitor here. And then it has an open, $open, and then there's a $close. Oh, that's inside here. So this, there's the close right there. Sorry, I didn't scroll over far enough. That was the problem. With the star saying, okay, now there's a number of these guys here, binary Expr, visit binary Expr, and then the types. So the types are right here. They just get moved here. Binary is this guy's name, and then binary Expr is this guy's name, and then all the traits get put together here. We see trait visitor, which is going to be Expr visitor in this case, and then we have all the visits and the accept. So I see how it all gets put together. The only reason I'm not going to just yoink this into my code base here is that I'm not sure if this is the final form, right? And hacking macros is not going to work for me because I don't know macros well enough. I mean, I can interpret what this is doing, but generating one on my own is a little beyond my skill level right now. So we're going to keep this in our back pocket and then see how this goes, and then maybe we can do is adapt this to whatever changes we need to make in the future. All right, so the next thing that this document does is it creates a pretty printer, not very pretty printer, just to test that this is all working properly. So this says when we debug our parser interpreter, it's often useful to look at a parsed syntax tree and make sure that it has the structure we expect. We can inspect it in the debugger, but that can be a chore. Instead, we'd like some code that, given a syntax tree, produces an unambiguous string representation of it. Converting a tree to a string is sort of the opposite of a parser. It is often called pretty printing, when the goal is to produce a string of text that is valid syntax in the source language. That's not our goal here. We want the string to very explicitly show the nesting structure of the tree. A printer that returns 1 + 2 × 3 isn't super helpful if what we're trying to debug is whether the operator precedence is handled correctly. We want to know if the plus or the star is at the top of the tree. To that end, the string representation we produce isn't going to be LOCKSS syntax. Instead, it will look like Lisp. Each expression is explicitly parenthesized, and all of its sub-expressions and tokens are contained in that. So given this syntax tree, it'll produce star minus 1, 2, 3, group 4, 5, 6, 7. Not exactly pretty, but it does show the nesting and grouping explicitly. To implement this, we define a new class. Okay, so what we're going to do is we're going to try to write a this Ast Printer, which will use the Expr code in order to dump out a parsed tree, right? So let's see if we can implement this. I guess what we can do is just create a new cargo, new Ast Printer, and just copy over this over here, and then we can just test it out this way, right? I don't know what they were intending to do with this. It is in the locks, so I don't know if they're intending to maintain it indefinitely or not. Rafael Luba, thank you for the raid. How was your stream? Was it good? The Jai crew is back. Yay! Welcome, Jai crew. Do you have emotes for Jai? I'll have to check those out after my stream if you do. Okay, so what we're going to do is take the Expr that we generated and create a new a pretty printer for it. So we need to implement the visitor pattern. So we'll create a new struct. Rafael says, I spent way too much time wrestling with the libclang API stupidness. Flailing at code. Oh, that's a good one. Whose is that one? Oh, okay. Nice. I like that. I'm going to have to use that on ToggleBit stream. Yeah. All right, so we have an Ast printer, but it doesn't do anything. So I think we can just do this, right? There's no data in it. All it does is have a print method, which returns a string. So it's not a print method, it's a stringify method. All right, take care, Raphael. Thanks for the raid. So we're going to do a print of an Expr. So we need to actually mod Expr, use Expr star, and we can just pull this up here. So this is what our Expr looks like. Official Catman says, "Is this Vim?" Yeah, it's a variation on Vim called NeoVim. So we have fn print, which takes in an Expr, and I'm going to, I guess, by reference, and returns a string, and we'll just say Expr accept self. Oh, it just needs a self then, right? And then hopefully, oh right, the accept returns a result. So maybe we can just return that result of string and locks error. For Expr visitor, right? A string. I guess we're doing a string. Is there a self type that you can use off of here? Official Catman says, "Do you VS Code?" I do not VS Code. I've been using Vim, VI, NeoVim for ages, and that's the most comfortable for me. Oh, thank you for the follow. Oh, and Pro Table Flipper. I missed your follow as well. Thank you for the follow, Pro Table Flipper. Okay. Let's see. Yeah, can we do self here, or maybe there's some thing here that we can just refer to this type without having to use the word string again. I bet you there's a way to do that. All right, so if we do this, oh, this is actually not part of this. This is impl Ast Printer, right? Because we're not to impl the Expr visitor, we can only put these things in here, and that's what these are. All right, so fn, is it binary Expr, which takes a self and an Expr binary. Oh, sorry, binary Expr, and it returns the result of string blocks error. And this calls a function called parenthesize. And we're going to pass in the lexeme, the left, and the right. So I guess we're going to be writing parenthesized. Yeah, right down here. Okay. So then the same thing for grouping, literal, and oh, this one's okay. This one goes to grouping, literal, and unary. Okay, and then what we pass in is going to change as well. So this is just going to be Expr expression. This is different. So this is, if Expr value is null, return nil. Of course, we can't have a null. Did we make it an option? We didn't. We made it an object. Maybe this needs to be an option. If it could be null, then we have to have a none, right? So let's change this to option. Oops. And then we'll have to remember to change it in our generator code as well. So we can say if Expr is none, no, Expr value is none, then we're going to return nil to string. And then, oh, hang on, I just got a text from apologies. So then we return nil to string. Oh, this got to return. Otherwise, we're going to call value to string. Okay, self. Oh, okay. So we can just say if let some value is equal to Expr value, right? Then this, else this. And then we just say value to string. Oh, Vidal, thank you for the follow. Okay, so what's next is we get rid of the left on this side. So now we need to write the parenthesize part, right? I can't check this yet because parenthesize doesn't exist. Oops. Oh, I forgot all the arrows on every single one of these. Oops. Oh, we don't have error. Do we need error? Oh yeah, for locks error and token. Okay, so I got to copy those guys over as well. locks ast, source error, and token. Wow. A lot of work. All right, so why is this unable to find? I just copied them over. Oh, you know why? Because I didn't mod them. Mod error mod token. Let's do that. All right, we still have 11 errors. Oh, and token. So I basically have to copy the whole thing over. Like that. What else? What else is missing? Locks error. Oh, I got this backwards for Ast Printer. Grouping. Still 14 errors. Expr.accept is method not found. Okay, so Expr should have. So did I get this wrong? They should all have an accept. Yeah. Oh, it's not pub. No, it's not pub. Okay, so that's a problem. Okay, so we made two changes so far. We made the value an option, and we made this pub. It's still not found. No method name parenthesize. Yeah, we can do that, right? Let's stub that out. Parenthesize. Oh wait. Okay, this is kind of annoying because parenthesize has multiple. Parenthesize is polymorphic. Oh yeah, look at that. Okay, so we're gonna have to hack that together. What's the way to do this? I guess we could have a 3, a 1. Oh, this is a group. I forgot this here, group. So parenthesize binary, parenthesize group. And this should be an OK. And then this should be parenthesize unary. Right, and then we just write one of those for each one of these things here. Or I wonder if we can just pass a vec. Wizard says you could take a slice. Yeah. So we could just do this. Right? Because each one of them starts with a string, and then there's zero or more, one or more entries. So we could just say this and then say self, and then what are we calling it? Name, and then a vec of Expr box Exprs. Yeah, left and right are box Expr. Is that going to work? And this returns a result string locks error. And then for now, we're just going to say nope to string. Like that. And by the way, hi Misery. I started off this stream by taking a look at your macro, which blew my mind yesterday. I can read it and I understand how it works, but this is not something I can yet generate on my own. So I was very impressed by this. I haven't pulled it into this repo yet, though. And actually, this is a side repo. We're just trying to get the Ast printer working. Oh, we're down to only 2 errors. Oh, you can't do you can't do that. Oh, I forgot the name. Duh, Exprs. That's what I forgot. There we go. And now except still doesn't work. Oh, and then all these parenthesized. All right, I've got to change these back. All right, still 13 errors. Wow, 13. Oh, I probably, okay, I spelt it wrong. Parenthesize. Make sure I spelled all these correctly. But that doesn't fix. So now we're down to 15. Oh, what did I do? Oh, these are private. Okay, so I got to switch all these to public. That's annoying. Okay, what's the next issue? We got 8 more errors. Method not found still. I don't get that part. And wait, I just changed these, didn't I? Expected stir found struct string. Oh, that is a string. Okay. And it means I have to toString this guy. Okay, we're down to 6. Expected reference. Okay. Down to 3, and then we got to figure out why this is not working, and why those are still private. Oh, in token. Oh, so make this pub, or I could make a getter function for it. All right, so now why isn't this? This is an Expr. Oh, I have to actually decompose it, don't I? I can't just say Expr. Not token, Expr. So here, I have to say impl Expr and put in a decomposer pub fun accept self result t locks error. Right, and then this has to say match self. Expr binary. Self x. Binary expression is going to be be accept. And then the other 3. Oops. This is grouping. Literal. Unary, and this will be grouping, this will be literal, and this will be unary, and then change these guys as well. Okay, so now there's an except there, supplied 0 arguments. Oops. Wait, what gets passed in? The visitor. Oh, we need the visitor. Ah, so this takes an Expr visitor. Right? So this will be self Expr visitor. I guess I can do that and then put self here. Oh, the self doesn't need to be passed in. Almost there. Help, add din keyword before this trait. Okay, I can do that. Now we're down to 7. Oh, move. Okay, so we do that. I guess we can do this, which means that this needs to be an ampersand. Wow. This is finding a lot of issues, right? This needs to be that. And now we have 5. Oh, and then these all have to be, wow. These all need to be ampersanded. Three errors. Expected slice found struct vec. Do I just do this then? Nope. Expected struct box found ampersand box. Oh. Okay. All right. Okay. The 64 warnings are probably all the things we're not using, but at least this builds. All right, so now we need to write this part here, parenthesize. And then apparently we can build up a brand new one this way. But all these references are getting me worried now about how we're going to manage lifetimes in the real thing. But let's see what we get here. So string, no, let mut builder equals string from this. Actually, we can just do it this way. Format, bang, open paren, and the name, right? And then for Expr in Exprs, I guess it's already a reference. Builder append space and that. So builder equals format bang, builder space this, which is going to just be Expr accept self. And then after that, builder is format bang, builder close paren. Like that. And then OK of builder is the return value. Is that going to build? Nope, we got an error here. Oh, we have to check it. I guess we can just question mark it. Okay, that builds. Now we're up to 57. From 64 down to 57. That's good. So it takes a name and a list of sub-expressions and wraps them all up in parentheses, yielding a string like open plus 1, 2, close. Okay. Note that it calls except on each sub-expression and passes in itself. This is a recursive step that lets us print the entire tree. We don't have a parser yet, so it's hard to see this in action. For now, we'll hack together a little main method that manually instantiates a tree and prints it. All right, so that's down here. Let expression equals. Okay, so here's where we're going to fail, right? And let's take a look again at our Expr code. All right. So we need to generate an Expr that has a binary. So how is this going to work? So it's going to be Expr binary, which is going to have a binary Expr in it, which is going to have I guess this is left token and right. So left is going to be Expr unary, right? And which is going to be a unary Expr, which is going to take an operator, which is a token, token type is going to be, let's take a look here real quick. Token type is going to be minus. Well, let's see. Is that token? Oh. Yeah, T type. So token type minus. And then the lexeme. Oh, all these need to be pub, right? If I'm going to try to set them here. Lexeme is going to be minus.toString. Literal is going to be none. And line is going to be 1. So that takes care of the unary Expr's operator, and now we need the unary Expr's literal. I don't know why that's not lining up. And a literal is just a box Expr. Oh, this has to be box, right? And so does this guy, box new. Expr literal. Open paren. Literal Expr. And a literal Expr is going to just be sum 123. And I have to put the 0.0 because it's a double, or it's an F64. So that's that. And that's the box. And now I'm lost in terms of my bracing here. There's unary Expr, right? And then unary, and then the box. Okay, so that's left. Then the operator is a token. T-type token type star. Lexeme is going to be a star toString. Literal is going to be none, and line is 1. Wow. And now I've lost my train of thought here. Okay, so that's the operator, and then the right is also going to be basically, oh, it's a grouping. Okay, so it's a box new Expr grouping of grouping Expr, which just contains a box expression, right? Box new Expr literal. Literal Expr value sum 4, 5, 6, 7. That, then that, and that's the whole binary expression, and that closes that, and that's a semicolon. Wow. And then we should just say Ast Printer print expression. Oh. Okay. Yeah. So we just say let printer equals Ast Printer, and then printer.print expression. I guess with a reference. Does this build? It did not. Try adding a comma here. No. Okay, maybe, yeah. Okay, it did like literal Expr. Oh, grouping Expr is this. Wow. Grouping Expr expression, colon. There we go. And then this here, this here, this here. This is hard to read, isn't it? And token type is undeclared. mod token type, use token type star. Oh, I already had it. Okay. And not found in the scope, so we're gonna have to use token. Token type : star. Literal. Oh, Unary doesn't have a literal? Oh, it has a right. Oh, it's a num. Okay, object num. And then it's the same thing for here, right? Object num. Wow. This keyboard's killing me. Okay. Okay, that built. It didn't print anything out because I didn't actually print it. I just returned a string. All right, so println, bang, this, that, there. Unwrap. Okay, look at that. Star minus 1, 2, 3 group 4, 5, 6, 7 and then 2 close parentheses. Okay, so that worked. And now I need to take a really quick break. Apologies for this. This is unusual for me. I did create a slide though a while back for it, so let's see how this goes. BRB. Okay, I'm back. Apologies for that, and I will have to remember to edit that out of the video I post to YouTube. I'll probably forget. Oh well. All right, so this works. And now it says you can go ahead and delete this method. We won't need it. Also, as we add new syntax tree types, I won't bother showing you the necessary visit method for them in Ast Printer. So, why did we do this? I guess we did it just to show that it's working and how to use it. Although it is very awkward, isn't it? The way we build this stuff up. So I'm like I said before, I'm worried about how this is going to play out in the real thing. All right, so we have some challenges. Earlier I said that pipe, star, and plus forms we added to our grammar meta syntax were just syntactic sugar. Take this grammar. Message says it's easier to parse them from a string instead. Yeah, so hopefully the way we have to build this up is going to be pretty obvious from the code. So, you know, fingers crossed this is all just going to work. So this says take this grammar. Expr is Expr, or identifier. Number, produce a grammar that matches the same language but does not use any of that notational sugar. Johanna says, are you familiar with C# expression trees? It looks like we are doing that. I am not familiar with C# expression trees. I poked at C# a little bit a long time ago. Maybe 5 years ago now. But I really didn't have any projects that used it, so I never really got into it. So let's take a quick look. I'm going to keep this tab open, Wizard, because we're probably going to come back to that. C expression trees. What does this do? Expression trees represent code in a tree-like data structure. Okay, so what we're doing is we're going through this crafting interpreters book, and we're going to be ending up implementing a lot of stuff that already exists. And the point of doing that is to learn how it works so that when you use it under the covers, you understand what's going on down there. So yeah, I think Rust has a few parsers, right? Rust. Yeah, it's parser generator, and then there's a few crates. Rust parsing trait. Crate, and not trait. And where the hell is the search thing on this? I can never find it. There we go. Parse. Pem. No, these aren't the ones I was thinking of. There's like pair or something like that. I forget what it's called now. But it's got a decent parser. So 2, the visitor pattern lets you emulate the functional style in an object-oriented language. Devise a complementary pattern for a functional language. It should let you bundle all the operations on one type together and let you define new types easily. SML or Haskell would be ideal for this exercise, but Scheme or another Lisp works as well. I will pass on that particular challenge. So in RPN, the operands to an arithmetic operator are both placed before the number. So 1 plus 2 becomes 1, 2 plus. Evaluation proceeds from left to right. Numbers are also pushed into an implicit stack. An arithmetic operator pops the 2 top numbers, performs the operation, and pushes the result. So this becomes this. Define a visitor class for a syntax tree that takes in an expression and converts it to RPM and returns it the resulting string. That sounds like an interesting challenge. Once you have the tree, right, you're basically just walking the tree, and RPN becomes a specific type of tree walk. You know, it's a postfix. So it's left, print right, print node, done. And you just recurse for each node. You know, this says print left, print right, print node, done. So this goes to here. So that's the first thing you do is print left. The first thing you do is print left. So 1, 2, 3, print right, there is no right, print the node, minus, done. And then come up here, prints this, and then prints this. So RPN is just basically a tree walk doing left, right, node. And this is doing something similar because it's coming out with this sort of Lispy kind of thing. So it's an interesting exercise, but not for the stream. So now we're going to get into parsing expressions, which is, I think, where we're going to find out how good we did with our design for the Expr code. Let's see first what the differences are, because we need to fold those into our code generator. What source? All right, so, oh yeah, I made everything pub. That's going to be annoying because it kind of breaks the whole separation of concerns thing. And then I had to create this, right? So this will need to be added to our code generator, and then all the pubs need to go in there. So let's do the pubs first. Mod, because those will be relatively easy in comparison. So I think this is just, these are the pubs, right? The visits? No, the accepts were the, there we are. So let's get rid of this comment. Actually, we don't need that anymore. And this needs to be a pub. And then all of the fields in the struct need to be a pub. Right? So let's do that. Let's see if this builds. And then we can do a diff. Yeah, okay, so we cleaned up most of it. Oh, and then that's right, this needs to be an option object. So that's something we can change up here. Visitor says impl expr accept 2. Yeah, this whole thing. Right. Yeah, let's get that next. And where should we put that? I guess we could just, after we implement all this, we can just do it right here. Let's pull it in so I can see what it looks like. And then we can write it out. So we're going to start with write bang, impl, expr, open brace, new line, oh, file. And then expr is going to be just the base name. So we've done this line. Now we need to do this line. Write file. Oops. Forgot the commas. Pub fun accept t. Self expr. Oh, not expr. This visitor is going to be din. And then we can just put base name actually here, right? Visitor t. Does Rust do multi-line strings, or am I going to have to just string this whole thing out here? And then results t locks error open brace, and then this will be base name to lowercase. Yeah, and then question mark semicolon. It would be nice to break that into multi-line string. I don't know if Rust does that. Okay, for t in tree types. And now, we have to do the match self. Right, bang, file, comma, match self. New line. Oh, did I forget the new line here? I did. And then this is close question mark semicolon. Okay, now for X in tree type, or T in tree types, we have write, bang, file, and then Expr, which is base name. Actually, I'll just do it this way because it makes it shorter. And then the type. This doesn't have to be BE. We can just call it X or visitor. Let's call it V for visitor, and then v.accept. It's just going to be this visitor. And that's going to be a 2 lowercase on that one. Open, close paren, comma, new line. Lord Msd. Hi, and thank you for the follow. And Mr. Anderson OX. Mr. Anderson Ox. Thank you for the follow. Is that a Matrix reference, Mr. Anderson? I can't do that guy's voice. Okay, and then we just need, for this we need base name. For this we need t.base class name, and for this one we need base name to lowercase. Right? That loops that, and now we do a write bang file. You have the match self, new line. Oops, I forgot the question mark. Quote. There we go. And then one of these we do for X, and one of these we do for X. And that does this whole thing. Let's do 2 new lines here. Oops, I messed that up. Good. Okay. So I think that does that. Let's see if this checks. 15 warnings. But that's all of these things, right? Yeah. Okay. Let's do the diff now. Oh, I got it almost right. Oh, yeah. No, this is right because I changed these from BEs to Vs, which is fine. Everything else looks like it matches. And then there's an extra blank line in my code, but that's fine. I don't mind that. So this seems to be working okay. Git status, git diff. So yeah, we changed this to option. We added all the code to generate the impl for the accept. And then we made a couple of different things pub, right? And then deleted this comment. Okay, that's good. Lord MZTE says, why are you writing Rust code that writes Rust code? Well, so because I don't know how to do macros yet. This was Mizzard's macro to do exactly what we're doing, although it needs to be, we'll need to tweak, we would need to tweak it in order to get what we need with the thing. So what we're doing is we're going through this crafting interpreters book, and at the beginning of it, we took a look at what was required for parsing. And down here is where we're generating code. This is all done in Java, which we're porting to Rust. And this Java code generates Java code to pull into our interpreter. So that's what this is doing. We're generating Java code, which pulls into our interpreter. But we're going to get back to writing Rust code, which does locks in a second. Let me just get this checked in or committed. Add source. Lord says, oh no, it's not that bad, I'm sure. Update generator to handle, to fix issues found when creating Ast Printer. Okay, oop, git add, generate AST, there we go. All right, so let's parse expressions. Let's see how far, I got 1 hour left. Let's see if we can parse expressions. Grammar which knows how to control even kings by Molière. I don't know, I've heard that name before, oops. But I don't, he's like a French philosopher, right? Oh, he's a playwright. 1622, wow, pulling out the deep quotes. Okay, this chapter marks the first major milestone of the book. Many of us have cobbled together a mishmash of regular expressions and substring operations to extract some sense out of a pile of text. The code was probably riddled with bugs and a beast to maintain. Writing a real parser, one with decent error handling, a coherent internal structure, and the ability to robustly chew through a sophisticated syntax, is considered a rare, impressive skill. In this chapter, you will attain that. Oh, good morning, Just a Bubble. Your font color is different. It's easier than you think, particularly because we have front-loaded a lot of the hard work in the last chapter. You already know your way around a formal grammar, you're familiar with syntax trees, and we have some Java classes to represent them. In our case, we have Rust structs. The only remaining piece is parsing, transmogrifying a sequence of tokens into one of those syntax trees. Some CS textbooks make a big deal out of parsers. In the 60s, computer scientists, understandably tired of programming in assembly language, started designing more sophisticated human-friendly languages like Fortran and Algol. Is Algol a human-friendly language? Or am I thinking of APL? Is it being... Algol is a 3-star system, yes. Algol 60. What does it look like? What does Algol look like? Algol 60 syntax. What does the word transmogrifying mean? It means to change from one form to another. It's not a very common word, and if you're a fan of Calvin and Hobbes, you will have seen it a whole bunch of times. Mainly humorous. Transform in a surprising or magical manner. APL is not a human-friendly language. Yeah, but once you wrap your brain around it, then suddenly you can do all sorts of powerful things in very few characters. Mizzard says it's better than assembly, but nothing you'd want to use today, I think. Oh, about Algol? Yeah. Okay, this is C-ish, I guess. Or basic. Oh, Pascal with the begin and end, right? So maybe Algol was a precursor to Pascal? This is S Algol. I don't know. Yeah, this looks very Pascalish, doesn't it? Okay, let's get rid of Molière. Let's get rid of Algol. Alas, they weren't very machine-friendly for the primitive computers of the time. These pioneers designed languages that they honestly weren't even sure how to write compilers for. Wow. And then did groundbreaking work inventing parsing and compiling techniques that could handle these new big languages on these old tiny machines. Classic compiler books read like fawning hagiographies. That's a good word. adulatory writing about another person. Yes. Of these heroes and their tools, the cover of Compilers, Principles, Techniques, and Tools literally has a dragon labeled Complexity of Compiler Design. I actually have a copy of that book. It's a recent edition, or a more recent edition than from the 60s. But yes, it's the dragon book, right? Yeah. By Aho, Sethi, and Ullman. And here's a more up-to-date version where Monica Lam also contributed. And a Nightbring, a sword, and a shield branded LALR parser generator and syntax-directed translation. They laid it on thick. A little self-congratulation is well-deserved, but the truth is you don't need to know most of that stuff to bang out a high-quality parser for a modern machine. As always, I encourage you to broaden your education and take it further, but this book omits the trophy case. All right. So ambiguity in the parsing game. In the last chapter, I said you can play a context-free grammar like a game in order to generate strings. Parsers play that game in reverse. Given a string, a series of tokens, we map those tokens to terminals in the grammar to figure out which rules could have generated that string. The could have part is interesting. It's entirely possible to create a grammar that's ambiguous, where different choices of productions can lead to the same string. When you're using the grammar to generate strings, that doesn't matter much. Once you have the string, who cares how you got to it? Lord Mzidi says, if I had to write a complex parser, I'd probably use a nom crate. Yeah. There's a whole, we're not doing this to write a specific parser. We're doing this to learn how to write parsers. So, but yeah, I agree with you, Lord. Mizard says, I'm currently reading the Wiz series by Rick Cook, which references the Dragon book several times. Really? So I've never read that series. That's very cool. I know that there's, there was a list of books that ESR came up with that should be, and I can't remember the name of the book, but it had like a programmer who was transported to a magical land where writing software was the same as casting spells. So he cast the Emacs spell to write new spells. And I forget what that was, the name of that book. So when parsing, ambiguity means the parser may misunderstand the user's code. As we parse, we aren't just determining if a string is valid LOX code, we're also tracking which rules match which parts of it. That's the Wiz series? Really? Because I haven't read anything by Rick Cook. Well, at least not... Wizard's Bane. Oh, okay, yes. I read Wizard's Bane, but that's the only one I read. I didn't realize it was a whole series. Neat. Thank you for letting me know, Mister. I'm going to have to check the rest of those out. So here's the LOX expression grammar we put together in the last chapter. Yes, I remember this. So this is a valid string in that grammar, 6 divided by 3 minus 1. But there are two ways we could have generated. One way is starting an expression, pick binary, right? So expression, then binary. For the left-hand expression, pick number, right? Because binary now has expression operator expression. So we can pick number and use 6. So this expression would go to expression, then literal, then number, and pick 6. And for operator, which is one of these, just pick divided by, because that's what it is. And for the right-hand expression, we go to expression, and then literal, and pick binary again. And then for binary, we say expression to literal to number 3, operator of minus, and then expression to literal to number 1. And another is, right, to do the 6 divided by 3 first, and then pick minus afterwards. So you generate two different trees and you come up with two different results. Lord T says, oh no, there's a nil. Where's a nil? I missed the nil. Oh, this nil. Yeah, there's a nil. So Lox has a nil for values. In other words, the grammar allows seeing the expression as 6 divided by 3 minus 1, or 6 divided by the quantity 3 minus 1. The binary rule lets operands nest any which way you want, and that in turn affects the result of evaluating the parsed tree. The way mathematicians have addressed this ambiguity since blackboards were first invented is by defining rules for precedence and associativity. Right. While not common these days, some languages specify that certain pairs of operators have no relative precedence. That makes it a syntax error to mix those operators in expression without using explicit grouping. Likewise, some operators are non-associative. That means it's an error to use that operator more than once in a sequence. For example, Perl's range operator isn't associative. So A.B is okay, but A.B.C is an error. Okay. Yeah, so we understand precedence, we understand associativity. Right. Operator is less associative, so left groups before right. Assignment is right associative, so right groups before left. Without well-defined precedence and associativity, an expression that uses multiple operators is ambiguous. It can be parsed into different syntax trees, which could in turn evaluate to different results. We'll fix that in Lox by applying the same precedence rules as C, going from lowest to highest. So equality, comparison, term, factor, and unary. Right now, the grammar stuffs all expression types into a single expression rule. That same rule is used as a non-terminal for operands, which lets the grammar accept any kind of expression as a sub-expression, regardless of whether the precedence rules allow it. We'll fix that by stratifying the grammar. We'll define a separate rule for each precedence level. Okay. So expression is an equality. Equality will check comparison. Comparison will check return, factor, unary, and primary. You got to come up with all these names here, right? Instead of baking precedence right into the grammar rules, some parser generators let you keep the same ambiguous but simple grammar and then add in a little explicit operator precedence metadata on the side in order to disambiguate. I'm not sure I followed that 100%. Lord Mst says, really, ABC is an error in Perl? Impressive they've actually found a string that's invalid Perl code. Is that, yeah, okay, there you go. Very amusing, Lord. Okay, each rule here only matches expressions at its precedence level or higher. For example, unary matches a unary expression like bang negated, or primary expression like 1, 2, 3, 4. And term can match 1 plus 2, but also 3 times 4 divided by 5. The final primary rule covers the highest precedent forms, literals and parenthesized expressions. Okay, we just need to fill in the productions for each of those rules. We'll do the easy ones first. The top expression rule matches any expression at any precedence level. Since equality has lowest precedence, if we match that, then it covers everything. We could eliminate expression and simply use equality in the other rules that contain expressions, but using expression makes those other rules read a little bit better. Also, in later chapters, when we expand the grammar to include assignment and logical operators, we'll only need to change the production for expression instead of touching every rule that contains an expression. Okay. This I'll buy, right? We want to make sure that when we're doing the future work, we don't have to rewrite everything or refactor everything. Over at the other end of the precedence table, a primary expression contains all the literals and grouping expressions, right? And yep, we include nil. But notably, we also include this, right? Open paren expression, close paren, which loops us back to the top of the hierarchy. So anything in parentheses has its own hierarchy, which makes total sense. A unary expression starts with the unary operator followed by an operand. Since unary operators can nest, bang bang true is a valid if weird expression, the operand can itself be a unary operator. So unary is just bang or minus followed by a unary. But this rule has a problem. It never terminates, right? We have to stop it at some point. Remember, each rule needs to match expressions at that precedence level or higher. So we need to let this match a primary expression. This works because you could terminate it with a primary. The remaining rules are all binary operators. We'll start with the rule for multiplication and division. Here's the first try. A factor is a factor followed by one of these things followed by a unary, or it's a unary. The rule recurses to match the left operand. This enables the rule to match a series of multiplication and division expressions like 1 times 2 divided by 3. Putting the recursive production on the left side and unary on the right side makes the rule left associative and unambiguous. All of this is correct, but the fact that the first symbol in the body of the rule is the same as the head of the rule means its production is left recursive. Some parsing techniques, including the one we're going to use, have trouble with left recursion. Recursion elsewhere, like we have in unary, and the indirect recursion for grouping and primary are not a problem. There are many grammars you can define that match the same language. The choice for how to model a particular language is partially a matter of taste and partially a pragmatic one. This rule is correct but not optimal for how we intend to parse it. Instead of a left recursive rule, we'll use a different one. So a factor is unary followed by open paren, so any number of divide by or multiplied by unaries. That's what this star means. In principle, it doesn't matter whether you treat multiplication as left or right associative. You get the same result either way. Alas, in the real world with limited precision, round-off and overflow mean that associativity can affect the result of a sequence of multiplications. Now, this is an interesting point. In languages like LOX that use IEEE 754, the first evaluates to 0.006, while the second yields 0.006, a bunch of zeros and a 1. Sometimes that tiny difference matters. This is a good place to learn more. All right. We define a factor expression as a flat sequence of multiplications and divisions. This matches the same syntax as the previous rule, but better mirrors the code we write to parse LOX. We use the same structure for all of the other binary operator precedence levels, giving us this complete expression grammar. All right. So a factor is unary followed by the operator followed by unary. Term is factor followed by operator followed by factor. Comparison is term followed by operator followed by term, and so on. And so on is just this last one. This grammar is more complex than the one we had before, but in return we have eliminated the previous one's ambiguity. It's just what we need to make a parser. All right, so we're going to write a recursive descent parser. The whole pack of parsing techniques whose names are mostly combinations of L and R. We have LLK, LR1, LALR, along with the more exotic beasts like parser combinators, early parsers, and shunting yard algorithm, and packret parsing. For our first interpreter, one technique is more than sufficient: recursive descent. So recursive descent is the simplest way to build a parser and doesn't require using complex parser generator rules like yak, bison, or antler. All you need is straightforward handwritten code. Don't be fooled by its simplicity, though. Recursive descent parsers are fast, robust, and can support sophisticated error handling. In fact, GCC v8, Roslyn, and many other heavyweight production language implementations use recursive descent. It rocks. Recursive descent is considered a top-down parser because it starts from the top or outermost grammar rule and works its way down into the nested sub-expressions before finally reaching the leaves of the syntax tree. This is in contrast with bottom-up parsers like LR that start with primary expressions and compose them into larger and larger chunks of syntax. A recursive descent parser is a literal translation of the grammar's rules straight into imperative code. Each rule becomes a function. The body of the rule translates to code roughly like this. So we have terminals, non-terminals, an OR, which is an if or switch statement, a star or plus, which is a while or for loop, and a question mark, which is an if statement. I'm not sure what... Okay, so I think what they're saying is for this, to translate this into code, we look at this, and if it's a terminal, then it becomes code to match and consume a token, like a number, string, true, false, or nil. A non-terminal, which is going to be like factor, which is going to be a function. So we'll have a function called unary, a function called factor, and so on. An or alternative becomes an if or switch statement, right? So this is number or string or true or false or nil. So this will match. In Rust, we'll use match to match on these. A star, which means 0 or more, and plus, which means 1 or more, turns into a while loop or a for loop. And a question mark, which I don't see any question marks in here, which means I think is 0 or 1, right, becomes an if statement. The descent is described as recursive because when a grammar rule refers to itself directly or indirectly, that translates to a recursive function call. All right. All right, so now we're going to actually get to write some code. Yay. Each grammar rule becomes a method inside this new class. So we're going to create a parser. We're clean, right? Yep. npm source parser. And parser is going to pull in list, which in our case is vec, which is already pulled in, and we need token type. Use create token type star. All right, so we're going to create a parser, struct parser. I guess it has to be pub, right? Because we're going to need to create it from outside. It's going to take tokens, which is a vec of token, which means we also need token. There. And it's going to have a current. And then we'll impl parser. And this is just a new. Ooh. Oh. And it's going to return a parser. Okay, how are we going to do this? Because I want to pass in... I guess we can own them at this point? I don't know. Are we able to own them? I mean, do we do this and then... No, because if I do put a reference here, then suddenly we have to deal with lifetimes and all that kind of crap. Let's see if we can get away without it. See if we can pass ownership of this thing down into the parser. We'll see if we can get away with that. So like the scanner, the parser consumes a flat input sequence, only now we're reading tokens instead of characters. We store the list of tokens and use current to point to the next token eagerly waiting to be parsed. All right, so the current is just an index into this vec. We're going to run straight through the expression grammar now and translate each rule to Java code. The first rule expression simply expands to the equality rule, so that's straightforward. All right, so we can just say, and this is private apparently, expression, and we're going to have to take a mutable reference to self, right? Because we're going to be bumping this thing along, and this is just going to return an Expr. I'm thinking that we should be returning a result, right? Because if we get parser errors, we're going to have to end up doing that. So self-equality. Each method for parsing a grammar rule produces a syntax tree for that rule and returns it to the caller. When the body of a rule contains a non-terminal, we just call that other rules method. That's why left recursion is problematic for recursive descent. The function for a left recursive rule immediately calls itself. Okay, and then we hit a Stack Overflow and die. Yeah, that makes sense. The rule for equality is a little more complex. It's going to be a comparison followed by one of these two tokens followed by a comparison, 0 or more comparisons. In Java, that becomes this. And again, we have match. Lord Ms. T says, what Vim GUI are you using here? I'm just using NeoVim. I am using toggle byte. Oh, I already have that tab. Yep. Let me paste this into chat. So this is what I'm using with a few extra tweaks. I'm using ToggleBit's NeoVim setup with a few tweaks that are for me. Because we don't need that anymore. We don't need Dark Reader anymore. This is my other thing. Oh, we're going to get back to this next week. So I'm going to like alternate 1 week of crafting interpreters and 1 week of we're working on a roguelike. So that's going to be fun to get to. We'll do that on Monday. So we have this. So we're doing an expression. I'm just trying to figure out what match is doing. Oh, and match, of course, is doing multiple. Yeah, so we can just use the vector again like we did with the other one, the parenthesize thing. Okay, so this is equality. It's going to take immutable reference to self. Return results. And it's going to call comparison. Self. Oh, let. What is this doing actually? So it's calling comparison and then saying while we match this, we get the operators calling previous. I guess that's previous match. Then we call comparison again for the right side. And then we reset Expr to be the Expr but with the new binary Expr in it. Lord Misty says, your config is very minimalistic. There's no LSP integration or anything. I actually have LSP running in the background. It's running there. I just don't have it telling me code completion and stuff like that. That's all disabled. So actually I don't know why what it's doing in the background other than just sitting there taking up CPU resources. There's got to be something I can use it for, right? I don't know. So if we need to reset Expr each time, this has to be mutable. So we'll call self-comparison. Oh, self-comparison question mark. And then say while self is match. And we're going to have to pass in a vector of token type bang equal or token type equals. I renamed it from equal to just equals. So if it's one of those matches, then we're going to say let operator self previous and then let right equals self comparison, right? And then Expr becomes, oh, how did we generate this now? I've forgotten already. Source main. It's a little complicated, right? So we have to say box new Expr binary Expr, right? And maybe this is something we can add to the Expr impl to create these for us so we don't have to be so complicated, but let's see how it goes first. So the binary Expr is going to have a left of the old Expr. It's going to have an operator, which is just that, and then it's going to be right, assuming that self-comparison returns a box. Oh, yeah, so assuming it returns a box Expr, but it isn't, right? We're just returning Expr. Should we return a box Expr? No. No. Okay, let's do this then. So box new Expr, and then right is going to be box new right, like that. That's interesting. And then we're going to return Expr says okay Expr. Okay. So let's step through it. The first comparison non-terminal in that body translates to the first call to comparison in the method. We'll take that result and store it in a local variable. Oh, Lord Let's see, says also no auto closing braces. That must be really annoying. Yeah, so if I say like println print bang, I open print, it doesn't automatically do the close print and then put the cursor right where it should be. So I started programming before that feature was available, so I guess I'm just used to it. I guess. I could give it a try. I don't know how to enable it. If you know how to enable it real quick in NeoVim, I can turn it on and see what it looks like. Or see how I play with it. So the first comparison is non-terminal, right? So we call it comparison. We take that result and store it locally. Then the loop in the rule becomes a while loop, and we need to know when to exit the loop. So we find either a bang equals or an equals equals, and if we don't see one of those, then we must be done. So we use this handy match method. So let's write the handy match method. Except I have to call it isMatch. I guess it doesn't need to be a self, right? We're just matching on a list of token types. Right? And we're just returning a bool. For t in types. Oh. Check. We're going to call check. Oh, I guess we do need self then, right? Because check is a member function as well. Self.check t. Oh, if. So we're doing the same kind of advanced thing that we did in the scanner, right? It's not built in. You need to install a plugin. I may already have the plugin and just have it disabled. I don't know. Is it in one of these plugins? If so, then it's just off. All right, so if self check t, then self advance and return true. Otherwise, return false. And Clippy will complain if I put return there. Okay. So this checks to see if the current token has any of the given types. If so, it consumes the token and returns true. Oh, that means it has to be mutable. Okay. Otherwise, it returns false and leaves the current token alone. The match method is defined in terms of two more fundamental operations. The check method returns true if the current token is of the given type. So if check. Well, this just does a peek, so this does not have to be mutable. Type. Oh, and I can't use that. T-type. Token type. And it returns a bool. If self is at end, return false. Oh, we can just say false or just else. Return self peak. Type is type, right? So now we keep pushing this the code further and further. Now that we have this, we need to write advance and is at end. Lord Mincy says, I don't think any of those plugins do auto closing. All right, well, that's something we can take a look at real quick here. And Vim, not autocomplete, auto parenthesis. Oh, I see. We could just do it this way, right? Let's try. Let me try that really quick. I know remap. Open brace. Left. So now if I say, yeah, okay. Pretty weird you're not using a plugin manager. Let's see, what is this using actually? There's got to be some some management somewhere. Yeah, I know. Okay, so this works for me. I guess I've never needed really plugins, and I only started doing this when I wanted to get quick compiles in my workflow. So right now I have it set up so if I hit Control D, it saves everything and runs cargo check and generates the quick fix list. It seems to work. All right, so we have advance, which doesn't return anything. Oh, see now what happens is if I do this now, right? Let's do that again. Fn advance self. So now there's the close paren. If I hit close paren, it puts in another close paren rather than stepping over it, right? The init script just manually downloads the plugins. That's right. It's partially Lua. Just a Bubble says, that doesn't seem healthy. To be honest, that config is kind of jank. All right. So I should call my stream Janky Stream. It's going to take me a while to get used to that. So if I'm on a closed brace or a closed paren or a closed bracket or whatever, it should, when I hit that, it should automatically just do that. All right, so what does advance do? If not self is at end and self current plus equals 1. Oh my God. And then return. Oh, this returns a token. I'm never going to get used to that, Lord Mitzi. I should write my own config. Well, I mean, I kind of looked over toggle bits and fixed it up or modified it to my liking. Just a Bubble says, I fixed my config yesterday. Oh, is your config on GitHub, Just a Bubble? I'd like to take a look at it. All right, so now we have is at end, peak, and previous. Let's write these guys. Is at end, takes self. Oh my God. And returns a bool. Lord Mincy says, I should write my own config from scratch. Yes. I would rather spend my time on stream doing this stuff than writing a config. I guess is where I'm going to go with that. So return peak type is equal to EOF. So we can say self peak equals token type EOF. Boom. And then we're going to write peak, which takes self and returns a token. And we're going to say self tokens get self current. And that's that one. That was easy. Fn previous self returns a token, and it just returns self tokens get self current -1. So we just have to hope that that doesn't go negative. All right. So this is Lord Mitzi's. Oh, you have your own GitHub clone, huh? Very nice. I'm impressed. So what... oops, I didn't mean to hit print. I meant to hit go back one. Okay, so you have plugins. And there's your LSP. Very fancy. All right, I will take a look at this off stream and see what bits and pieces I can steal from you. All right, so this is actually, I think we should be at the point where we can compile, right? We have everything defined, and we can at least see what's broken. Well, okay, we got 0 errors. We still have 15 warnings, but that's probably all those accepts and everything. So is at end checks if we've run out of tokens to parse. Peak returns the current token we have yet to consume, and previous returns the most recently consumed token. The latter makes it easier to use match and then access the just matched token. That's most of the parsing infrastructure we need. Where were we? Right, so if we are inside the while loop in equality, then we know we have found bang equals or an equals equals operator and must be parsing an equality expression. We grab the matched operator token, so we're talking about this code here. We did a match. This line does the grab the matched operator token so we can track which kind of equality expression we have. And then we call comparison again to parse the right-hand operand. We combine the operator and its two operands into a new Expr binary syntax tree node, and then loop around. So that's that whole while loop. Okay. For each iteration, we store the resulting expression back in the same Expr local variable. That's this guy here. As we zip through a sequence of equality expressions that creates a left associative nested tree of binary operator nodes. It's a good thing we read all the other stuff, because otherwise this would be meaningless, right? Parsing A equals B equals C equals D equals E. For each iteration, we create a new binary expression using the previous one as the left operand. The parser falls out of the loop once it hits a token that's not an equality operator. Finally, it returns the expression. That's here. Note that if the parser never encounters an equality operator, then it never enters the loop, right? Because isMatch fails. So all we have is this comparison. In that case, the equality method effectively calls and returns comparison. In that way, this method matches an equality operator or anything of higher precedence. All right. So we still can't run. Well, I guess we could run it, but nobody's calling parser yet. We have to link that into our main locks code. All right, so we're going to translate this into Java, and it's the same kind of idea where we pass in an array to match. So, okay, so we have expression, equality, and then comparison. With the result of Expr and locks error. And we're going to just call let mut Expr is self term, question mark. And then while self is match, token type greater, token type greater equal. And then we can do this. Oh, put a comma there. And do that, and then change this to, oops. Why is this not working? Less. Come on. Less. And then this goes like this, Right? Does that match that? Yep. Okay, I'll let our cargo format that for me. And then it's basically the same thing, right? As up here, except we changed comparison to term. Operator is self-previous, comparison becomes term, and we still generate a new binary expression and the return expression, right? All right, so yeah, I mean, that's basically the same thing. This grammar rule is virtually identical to equality, and so is the corresponding code. The only differences are the token types, the operators we match, and the method call for the operands, so now term instead of comparison. The remaining two binary operator rules follow the same pattern. In order of precedence, first addition and subtraction, and then finally multiplication and division. Okay, so what I can do is say, yank all of those lines and just put them in twice. And then for comparison, we're going to change this to term. For term, we're going to change this to factor. This also becomes factor. And then comparison becomes factor. And this becomes unary. and this becomes unary, right? So it's basically everything is the same. We're just generating a bunch of binary nodes. That's all the binary operators parsed with the correct precedence and associativity. We're crawling up the precedence hierarchy, and now we've reached unary operators. So now we need to make unary. Lord Mincy says, when I ported my config to Lua, it was more like, now I don't have to screw around with Vim script and can finally use properly. Well, okay. If you're going to get into language wars, that's something different. I'm not a fan of those. But the thing is that you have to do what makes you happy. And I like Lua's syntax. It's very nice and clean. I haven't played around with Vim script a lot, but I guess it gets the job done. So this becomes an if. Instead of doing a while loop, we're no longer doing a while. Oh, that's right. I have to change all these guys. So this is minus, plus, and slash, and star. I forgot about that. Minus and plus. And we get rid of those. And then slash and star. And get rid of those. Okay. So here's unary. Unary is going to say if self is match. And we can do this again. Token type. Or all the way down here. Bang. Or token type minus. Then we're going to do, the same thing. Operator is self previous. And then let right equals self unary. Oh, I forgot all the question marks on these guys, didn't I? And then, and this just returns directly. Okay, return Expr unary. And to create a unary Expr, we're going to do operator and then box new right, which means I have to put a right there, right? And then that. Oh no, unary Expr. Like that, semicolon. Right? Otherwise, we're going to just return OK self primary question mark. All right, now I have to go back and put question marks everywhere, and I'll probably miss a few. Self term and comparison. Okay. Hopefully I got those. Otherwise, the compiler will tell me which ones I missed. All right, so all that's left now is primary, right? Again, we look at the current token to see how to parse it. If it's a bang or minus, we must have a unary expression. Lord Mitzi says, didn't mean to start a war. No worries, no worries. Epic Blog says, the issue with Vim script is that it violates the principle of least surprise way too often. I can't, you're not wrong. All right, so in that case, we grab the token and then recursively call unary again to parse the operand, wrap it all up in a unary expression syntax tree, and we're done. Otherwise, we must have reached the highest level of precedence, primary expressions. There we go. Most of the cases for the rule are single terminals, so parsing is straightforward. Oh, I missed this thing here. The fact that the parser looks ahead at upcoming tokens to decide how to parse puts recursive descent into the category of predictive parsers. Okay. All right, so what we need to do now is figure out this final expression here. Oops, is going to be primary, which takes a mutable reference to self and returns the results. And now we're going to check these match. If self is match. I'm thinking if I should just write is single match just to avoid all this extra boilerplate around token type false. Right? If it's match of false, then we're going to return Expr literal of literal Expr of value of some false. object false, right? And now we're finally using, oh, no semicolon there. This needs a this, right? And this has a that, and then we're done. Okay. I think that's how you build it. And then we do the same thing for true and for nil. Right? And then we're going to check for number or string. If self is match, token type number, token type string. Oops. Then we're going to return Expr literal. Oh, all these need to be OKs, right? Dang it, I missed all of them. Okay, do you see why I'm not a fan of the code that automatically inserts a closing paren when you write an opening paren? Because now I write OK, open paren, and it puts a close paren in there. So now I have that to do. Yeah. And then this has to be an OK. And then up here, this has to be okay. Oh, this already returns. Yeah, so this is all good. It's all good. All right, so where were we? Primary. All these need to be okays. Okay, open. Let's see if I can do it that way. Nope, I can't. Stop hitting F1. Okay, and then okay. All right, so those are those. This will be okay, Expr, literal. And then we're going to say literal Expr. Value is going to be sum, self previous. Oh no, previous returns a thing, and then literal. We need to close the brace and then close that. Oh, that goes there. That one's that one, that one's that one, that one's that one, and then we have an extra one. Okay. Okay, we're good. So that's that one. And then we have left paren. If self is match, token type, left paren. Then we say, oh, then we grab the Expr. Okay. That gets the question mark. And then we have a function called consume. Okay. Expect closing brace after expression. Okay. I don't know what consume does yet. And then we're going to return okay, Expr grouping. So here's where we use the grouping thing. So now we shouldn't have any more of those warnings about unused things. So grouping contains what? Just an expression, right? Box new. And we have to close the brace first, and then close that, and then with that, and we're done. Okay. Oh, but we can't just fall off the bottom in Rust. We'll have to create a new error. And then what was Locke's error? I can just call error, right? Locke's error, error. And it takes a line number. Oh, what the hell line number are we on? Oh, we haven't matched anything yet. So we have the token, which has the line number. I'm just going to put in 0 for now, just because I want to get this going. Failed primary parse to string. Okay. So I think that'll satisfy Rust, right? And that just generates our locks error, and then that should bubble all the way up. Okay. The interesting branch is the one for handling parentheses. After we match an opening paren and parse the expression inside it, we must find a closed paren token. If we don't, that's an error. Oh, I see. So we match on left paren, we do the expression, and then the next token needs to be a right paren. But we don't have consume. Oops, I meant to hit W. Yeah, consume doesn't exist yet. We haven't written it. Maybe that's where we're going to get to next. But I'm out of time. Damn it. Okay. That's unfortunate. I was hoping we'd at least get something that could run. Can I just scan really quick and look for consume? Okay. Let's write this real quick, and then on my next stream we'll come back to we'll talk about syntax errors. 6.3. So we're leaving off on 6.3. Try to remember that. I'm going to try to. All right. So, and I'm not going to do this stuff. I'll just do what I did here. So fn consume self, right? Because we're going to call advance, which takes that, and then t type, which is token type, and then message, which is going to be a string. Oh, which means I have to toString this. And then what is this going to return? It's just going to return a token. Why is it returning a token? We don't actually use, okay, we don't use what it's returning. Oh, this needs to return a result, a token or a locks error, right? Because we're going to throw, quote unquote, an error if check fails. So if self check t type okay self advance, right? Does where's advance? Let's take a look at what advance returns. Yeah, it just returns token. Okay, so we'll do that. Else error locks error colon error, and then we're going to call peak. So peak returns, come on, we got to get this done quickly, a token which gives us a line number. So we can say let peak self peak, right? Which gives us our line number for this thing here, p dot. I just want to take a look at that structure real quick. It's just line. Okay. P dot line and message. Right? And that's that. That's the whole of consume. Does this build? It does. Wow. Okay, we're not using it, so I can't actually run this and see what it's going to do, but at least everything's in place and it compiles. Right? So we'll find out later if I got it right. Unfortunately, a big blog says Rust is never satisfied. Well, hopefully someday. But yeah, git diff. Oh, git add source parser. So we can take a look at all the changes we made. One of these days I'll get this right. Diff, there we go. Okay. So this is our parser. Clippy will warn us about all the fun, unused things we're using. Oh, and it did find a few other issues that we could fix up. We could use the slice directly, sure. Change this to stir. Okay. Oh, you can use right line instead of right with all the new lines. All right. Well, we'll fix those later. I'm out of time, unfortunately. So next week, starting on Monday, we're going to go back to our roguelike and look at magic items and item identification. This is the roguelike, which we were having fun with before. And now I guess we can just do this. Epic Blog says, ship it before you run it. YOLO. That's right. Ghost Steve, thank you for the last minute follow. And I am going to call that a stream. Thank you everyone for hanging out with me. I had a great time working on this crafting interpreters. And next week we're going to have a great time working on the roguelike. And then we'll go back to crafting interpreters after that. We'll keep going back and forth. Logminty says, what's your roguelike written in? It is written in Rust. Roguelike tutorial in Rust. Let me copy and paste. Well, I'll put it in chat, but I'm about to end. So I hope everybody has a great weekend, and I will see you Monday with roguelikes. Take care.